Well, there is a rising popularity of multi-threaded applications out there, partly because of multicore. Multicore hit the industry, and in the embedded systems industry, they are still in love with the sequential algorithms and the sequentiality of their deterministic system behavior. And marketing says, no, we're buying multi-cores. And don't tell me that you're only using one core. What are you going to do with the other 3 cores? We're going to buy you a CPU that's 1/4 as fast. That's enough for you. So they actually have to deal with the multi-core situation. Of course, they see the benefits, which is you can distribute the workload, you increase possibly responsiveness, you can create redundancy. So all these silver linings on the horizon that they love to see. And programming languages have begun to think about support of this, and I mean, Ada has done that 30 years ago, but other languages just now are really dealing in memory model definition and so on. But there is a new class of errors that comes about, namely these race conditions, and you'll see them in a moment. Deadlocks, everybody knows deadlocks from way back, and they are of course there, partly because of the concurrency behavior. And last but not least, the non-deterministic behavior of the program, where testing says, everything's fine, but the reality is it's not, okay? And let me give you a definition of what a race condition is. That's the traditional one. It basically says, if you have concurrent activities, some read a shared variable, and one of them writes them. And if you don't do synchronization, you're host. Okay, that's a race condition. If you want it in more formal words, well, it's up on the screen. Actually, this access to a single shared variable is usually, without synchronization, is usually called a data race. And I'll give you an example, okay? The example is very simple. We have a counter, we fork 2 threads, and each thread increments the counter. We wait till the 2 threads are finished, and then we print the counter, and 99.9% of the populations will say, what a stupid program. Of course, the result is 3. Right? Right. I mean, we've waited for them to increment the value. And what we don't realize, or what the general population doesn't realize, that sometimes the value is 2. Now, how did that come about? Okay? And in order to figure out how that came about, I need to go one level deeper. What actually happens on the machine? Well, on the machine, what usually happens is I'm loading up the counter, I'm incrementing the counter, I'm storing the value back into memory. And both threads are doing the same thing. So if on a single core I get hit by a context switch right after the first load has happened, and the other activity starts doing its thing, both of them load 1. Both of them increment 1, both of them compute 2 and store 2, and so the net result of that program is 2. What multicore added is simply that I don't need a context switch anymore for this to happen. Now the accidental concurrency of the 2 threads on different cores that modify the memory concurrently causes exactly the same problems. So in fact, these race conditions on multi-cores are going to be actually a lot worse than they are on single cores. Now, the race condition that I just showed you is termed a low-level race condition because it only involves access to a single variable. And for the last 10 years, technologies have been produced to figure out how to prevent the problem, namely, there's a log set analysis that says, we're going to check whether or not you're doing the right thing about synchronization. We're going to check what logs are being held while you're modifying the global variable, in this case none. Therefore, of course, these 2 counter increments are bad. I'm using C code here for an interesting reason. Well, we're analyzing C because it needs it most, but also because there is almost every time some intelligent person in the room that says, nah, on my architecture, increment is an atomic operation of memory, therefore this situation doesn't happen to me. Well, bytecode, virtual machines are an example of that. So this problem doesn't happen in Java. And for these guys, I have the advice, well, think again, because if your Java code gets compiled by a native compiler, you have the problem, right? And you're going to pay for the porting cost of finding the problem. So indeed, we know how to solve the problem. We put semaphores or some other synchronization mechanisms around these counter increments, and then log set analysis is very happy because it determines that the modifications happen under the same semaphore. Okay, and now I do have a guarantee that the outcome is 3. But of course, you knew all that, right? Actually, I doubt it, okay? A lot of people don't know about these problems of parallel programming. But let me go beyond, okay? Let me go beyond and look at the situation where all these locks are in place, and the synchronization on the single axes on variables is indeed controlled. And for the remainder of the talk, I'm actually going to assume that, because the formulas get a lot more complicated if one allows for bugs in that regard as well. But is all this enough? Okay. What about composite objects? What about structures that have functionally related components? Aren't there problems with that too? Is it indeed sufficient to control access to the single shared variables, or is more to be done? Let's look at an example which was designed according to the style guidelines of the company. It's almost a perfect example. It's a class whose components are all private, well hidden from sight. All the methods are synchronized. Therefore, how can there possibly be a problem? And yet there is, right? We're looking at 2 threads, and the sequence over there is not necessarily immediate, but we set the x and y components of our point in 2 different threads to either 3, 6 or 4, 5, and then some other thread, or this one thread actually gets the values. And stupidly, we get again a context switch, respectively, a true parallelism on the multicore right after we have gotten the x value. And of course, as a result, we get these 2 values, 3 and 5, which is kind of a surprise because there is no way of setting these 2 components in the program to 3 and 5. So this is really bad. And it looks like, well, what do I care about numbers? Well, I'll make it more stringent. I'll make it more stringent than you. Suppose the x is your foot on the brake? And suppose the y is, we're going to shift into gear. You certainly do not want a logic in your program that then actually realizes, was your foot ever on the brake in the past, but maybe no longer? And let's shift, okay? And you know what I'm talking about. Not that that one was a software problem, but that's exactly what you can cause if you don't watch out for this problem. Yet, my log set analysis says everything is fine. Every access to any variable that might matter is indeed protected by the same lock, namely the lock over the object of that point. This is a violation of atomicity, and this is the first problem that we're going to deal with. It's a non-atomic protection fault. There is a formal definition that goes back about 10 years. Artho formulated it, and basically it says, if we have a thread that accesses the shared variables partially, like this one did with the getX and the getY, and we have a thread that sets the variables together, a larger set, and that was the set XY. If that ever happens, so that the partial accesses can diverge because one of them is writing, then we have that particular problem. Okay? And well, we need to detect that situation. We better detect that situation. Here's another example. Let's look at the thread B first. Your wife is going to the bank and deposits money, and it's done on the logs, of course, so everything is fine as far as log set analysis is concerned, and she deposits €1,000. Meanwhile, you're at the bank, and your account before the deposit was €50, and you want to withdraw 20. And the logic that runs is, well, let's look at your balance. 50, okay, we better check that you do have the money, or else we don't give you the money. If your balance is greater than the amount, then we proceed to subtract 20 from your account of 50, yielding 30. And of course, you know what's happening here. Your wife's deposit of €1,000 just goes down the drain. That is to say, into the balance sheet of the bank, because what happened here is a context switch that hit right after the unlock of the withdrawal, and then the deposit happened, and as a consequence, your balance at the end of these two transactions, if you will, which there aren't, is indeed 30 instead of 1,030. This is called a lost update. And again, we want to discover that. Remember, log set analysis says everything is fine, because every access to a shared variable is indeed protected by a log. We can define a lost update as the existence of a value dependency from what will be termed a view from a code segment, a log-protected code segment, into another log-protected code segment where the writing of that same variable happens while there is a concurrent thread that modifies the shared variable as well. And you saw this in the example. There were 3 code segments protected by the logs, 3 views, and the players are identified here. Detection mechanisms. In order to detect the non-atomic protection issues, we need a log-variable relationship, and that relationship Arthur already worked on, and it's called a view. Okay, the set of these variables is called a view. And to detect the lost updates, we need to add value dependencies to the information. Now, sorry, we gotta produce a few formulas, and I'll talk you through the formulas without explaining them by mathematics. There is the notion of a critical path, and intentionally path, not region, okay? Path, a part of the execution sequence that begins with a lock, with the locking, gaining a lock, and that ends with releasing that lock, and whatever happens in between, without also unlocking prematurely, it constitutes the critical path. What the view is the set of all variables that get accessed as part of this critical path, and these views are parameterized, of course, by the lock that we're obtaining, by the thread that's executing it, and by the code segment itself. We extend that definition in our work by adding the access kinds, which is an easy extension to remember whether it was a read or a write. That's useful, and I never understood why Arthur didn't take that. But we also extend the view by adding locks that are obtained while we already have a lock. And the reason for that is the example that you just saw earlier, where we did the getX and the getY and the setXY, because maybe, just maybe, I wrote the program like that, okay? I have a synchronized that surrounds them both. And side remark, the paper and all its formulas assumes proper nesting of synchronization, like you have it in Java, like you have it in Ada, but of course you don't have that in C if you're working with semaphores. Generalization is straightforward, but it's not reflected in the equations. Nested views, okay, the picture looks like that. It's like an eggshell model, okay? I have my inner views with the log EL, those are the synchronized methods, but I have an outer view with a log EM, that was the synchronized block that we saw. And obviously, we're now okay. okay, because we no longer can read X and Y inconsistently, which incidentally here is the programming answer to the problem. In order to build that into the detection mechanism, we need information about new containment, so we can define a parents relationship that says, and I apologize for a reformatting that has happened on the transfer of the PPT here, a parent relationship that says, if within a view you're gaining yet another lock, you obviously have created sort of a child lock. You're now at the inner lock in the egg-shelled model. And the outer view is called the parent. So if the locking operation for the inner view is part of the statements of the outer view, then the outer view is a parent. If we know parents, then we can exclude these non-atomic protection fault error reports by looking for a shared parent. So first we look for the two partial access views, V1 and V2. Do they have a common parent? If they do, P1 equals P2. Then we're looking on the other side of the nested problem, and there are two cases there. One case is there isn't an eggshell around it. It's the view itself, the inner view, that has the same lock, and then we're golden. Or else you have the fully symmetric picture that on both sides there is a parent view over the same lock, and that's the second part of the formula to exclude that case as well. In order to reflect the view nesting, we extended the definition of views to include locks. Well, they are now part of the view too, okay? In which case this predicate locking operation is part of the statements of the view, turns into, is a lock in the view. Okay, it's an easier check. That's all there is. Incidentally, if one generalizes this to C, then the parents predicate would also ask for the unlocking operation to be part of the critical path for the inner view. And down here, we would not remember locks, but we would remember nested views. Detection mechanism. It's a data flow algorithm that is applied. It's flow, path, and context sensitive. So pretty sophisticated piece of implementation. And here are the data flow equations, which are pretty much the standard ones. If we see a lock operation, a view is generated. If we see an unlock operation, all views over the same lock end here. There is the out computed as the chain unions with the in minus the kill, that standard data flow equation. And the problem is a union problem. We union the outs of predecessor blocks to get the in of the subsequent block. This is a union of sets of view sets, not a union of views, and that makes the analysis path sensitive. The data flow actions, if we see a read or modify of a shared variable, we insert it into the respective view with an indication of what operation it was. If we see a lock operation, we add the lock to the view to get this nested view stuff going. And once we have a stabilized data flow solution, then we store the views away at the point when the view ends. Why path-sensitive analysis? This is a tricky problem here. Well, let's look at the left-hand side, at the right-hand side first. The views in thread 2 is easy, okay? It consists of the variable x and y of this global datum GL. And that's true for path-sensitive and path-insensitive analysis because there's really no, there aren't multiple paths. It's different for the thread 1. Thread 1, when you look at it path sensitively, then there is the possibility of locking, accessing X, con this false, we unlock. So there is a view on this path that contains only the x. Okay? On the other paths, we have an xy view, and we have a y view that's easily seen. Now, if we did a path insensitive analysis, we would merge views. And if we merge the x alone view into the x and y view, the result is, of course, the x and y view. Right? That's regular set merger. This is not what we're doing. We want to keep the information alive that there's a view on x alone, and this is done by merging view sets as opposed to views. I realize that that has, in theory, exponential complexity, but in practice it never happens, okay? Largely because people do not mess around with locks and unlocks in arbitrary places. They usually use them in dominating contexts. The remainder of the analysis is pretty simple. You just apply the formal definition and look for situations that apply to it. And Arthur provided a very efficient solution for the non-atomic protection problem, which we are now refining by filtering out these nested view situations by applying this no-nap error filter. For the lost update example, we're back in the bank. We're going to create these three views where the balance is being written, or both in the last case. And now we need to figure out whether there is a value dependency of V2 on V1, okay? Which in this case, of course, it is. It goes through the temp variable that is being created there. Once we discover that, and we're seeing that there's a write on the other side of the fence, then we know that we have a lost update in V3. The detection mechanism uses what we already have available, namely an SSA representation of the program. And if you don't know what that is, well, every variable use is related to its definition. And if it has multiple ones, there are funny nodes in the representation that unify that so-called phi nodes. And what we basically do is we walk that representation backwards, trying to find a write to a read of the variable, an origin, pardon me, a write of the variable that we're interested in, whose value influences the subsequent write in the V2 version, in the V2 view. So once we've determined these value dependency sets, then any concurrent write access of f in another view is indeed a lost update. And the lost update, unfortunately, got dropped off. PPT problem, you were right. Okay, sorry about that. Yeah. Implementation, standard compiler technology, except that it's global analysis as opposed to local analysis. Go through a front end, do a points to analysis, do a control flow analysis, do an SSA analysis, and now we walk into a log set analysis, that value dependency analysis that you just saw, and then the detection, the application of the predicates to the results to actually identify all the races, and ultimately we produce error messages. And thanks to our path strategy, we can actually tell exactly on which path the problem will arise in case the problem is indeed path sensitive, as in this one example that you saw. A few numbers, not that these numbers are very meaningful, but they do show that it actually was implemented and not just a paper exercise. And number two, they do show that this can be done efficiently, which is a bit surprising for for an algorithm that is theoretically of exponential complexity. And as you see, for 50,000 lines program, the analyses that I've been talking about here all ran in less than 1 second, and in one case it took 2 seconds to do the back traces, because the back traces obviously were a bit difficult, but the analyses themselves were in the below second level. SSA creates a fantastically efficient way of deciding value dependencies. Log set analysis, on the other hand, can be pretty expensive, but luckily that's not the subject of the talk here. Did we find races? Yeah, we did. In PFScan, there were in fact 3 non-atomic protection errors. Incidentally, when you look at these examples, few threads out there. It's really tough to find good public domain, interesting public domain software that is solidly behind threads, a zillion threads written in C. It's hard to find. Okay? There are a couple of benchmarks out there. Okay? There weren't all that many views. Okay? They did synchronization by other means. Views here really do rely on semaphores to establish them, or whatever the locking strategy might be that is being recognized. You see, incidentally, that the views can be fairly long, right, and fairly elaborate. There were views in this last example that included 53 shared variables as part of a locked axis. Probably a larger structure with that many data components. Conclusions. Only dealing in atomicness of single shared variables is not enough. Right? So you got to go beyond that. You need higher levels of abstractions for these error situations that can arise. They have been so far insufficiently characterized. You saw 2 of them, but there are plenty more, and we're actually working on developing several others to the point that we can discover them. And indeed, more work is needed along these lines. And the last sentence, it's really ultimately very difficult to determine whether a data race is intended. Some of them really are, okay? Or whether they constitute an unintentional and possibly disastrous element in the execution of a program. That's also a rather unsolved and unanswered question. And now I have time for your rather difficult questions that you might ask. Thank you.